Okay, continuing on with working with determinants, and we have for elementary row operations and determinants. And let's say if we have that A and B are square matrices, where when B is obtained from A by interchanging two rows of A, well, we're going to have that the determinant of B and the determinant of A will be additive inverses. And okay, just a case here. Okay, so if you have matrix A to be a 2 by 2 arrangement where we have the top row to consist of A and B, and the bottom row we have it C and D, and B we have it the other way around with C and D at the top, A and B at the bottom. We're going to have that the determinant values of these matrices would be additive inverses. And say if you have like the determinant of A, again, you have just in the conventional way, you have setting up A and B, C and D, where you have A times D minus B times C is going to be the determinant. And also through the lens of B, okay, the determinant of A is going to be the additive inverse. The determinant of B, where we have the negative, the determinant with the top row consisting of C and D, the bottom row we have A and B, and you have the negative of the product of C and B minus the product of A and D, and looking at distributing the negative sign over the difference of C and B and A and D, what was positive becomes negative and vice versa. And so this amounts to A times D minus B times C. And just looking at just what we have regarding the given matrix A as a 2 by 2. Okay, we have A consisting of 1 and 2 at the top, 3 and 4 at the bottom. And again, the determinant would be like 1 times 4 minus 3 times 2. But again, like through the perspective of putting it in terms of B, where you just have the interchanging of the rows, you would apply the negative sign of the determinant where we have 3 and 4 at the top, 1 and 2 at the bottom. And taking the cross products, again, we have 3 times 2 minus 1 times 4. And taking the opposite sign of the difference, again, that comes out to negative 2. Now, in terms of interchanging rows, you would not typically have this to come to mind in the case of a 2 by 2 matrix, but this would come as more of a viable option if you look at larger square matrices, okay, such as a 3 by 3. And say if you have, for this particular 3 by 3 matrix, okay, we have the top row, we have 3, 4, 7, middle row, we have 1, 0, 0, and 2, 9, and negative 5 at the bottom. And in terms of working with minors and cofactors, especially if you're fixated upon the coefficients at the top, you want to potentially reduce the amount of work that is done. And notice we have a couple of zeros in the middle row. And if we look at interchanging, let's say the top and middle rows, again, once you interchange the rows, you're going to apply the negative sign once the interchange is put into effect. So you have the negative of the determinant, where we have 1, 0, 0 at the top, 3, 4, 7 is in the middle, and we have 2, 9, and negative 5 at the bottom. And in this particular case, all right, so we're looking at the opposite sign, and we have of 1 times the minor of the first row, first column. So you have a 2 by 2 with 4 and 7 at the top, 9 and negative 5 on the bottom. And applying what we have here, so you have the opposite sign of 1 times. Okay, and we have 4 times negative 5 minus 9 times 7. And we got the opposite sign. Now, 4 times negative 5 is negative 20. And we have subtracting 9 times 7, which is subtracting 63. And the difference we have at negative 83. And applying the opposite sign, we had the result for the determinant of this 3 by 3 matrix to end up at 83. Now, looking at elementary row operations and determinants, okay, you might have some situations where you can have scalar multiples. And let's say you have that A is equal to, where we have 1 and 2 at the top, and instead of 3 and 4 on the bottom, say if you have 30 and 40. And what you can do here is that you can factor out 10 in reference to the bottom row. And if you do this, okay, we can say we have 10 jetted out, and we have times the determinant of 1 and 2 at the top, 3 and 4 at the bottom. And again, we're back to where we have the determinant to be negative 2. just for the 1, 2, 3, and 4, but for the whole thing, we have 10 times negative 2, so this will come out to negative 20. And also, if I look at, say, if I have negative 120 at the top, 30 and 40 on the bottom, okay, if you look at it, let's say if you factor out 10 once, and you can say that the 10 will be factored out from negative 120. And for what we have here, okay, so if I factor out 10, it'll be in one take, either for the top row or the bottom row. And let's say that if this is in reference to the top row, you have 10 times the determinant, where the top row you have negative 10 and 2. Bottom row, again, we still have fixed at 30 and 40. So you got 10 times, and you had the difference of negative 10 times 40 and 30 times 2. And so we have 10 times the quantity of negative 400 minus 60. And this amounts to 10 times negative 460, which comes out to negative 4,600. And if I were to have, let's say, just taking the 10 out, and let's say that, kind of like in the first example here, underneath the elementary row operations and determinants heading, let's say that we have 10 to be factored from 30 and 40. So your negative 120 would remain fixed. And looking at this combination of cross products and taking the difference, so you have 10 times what's going to be negative 400 minus 60, and we still have at negative 4,600. Okay, so if we're looking at, let's say if I were to factor out 10 twice, once in reference to 30 and 40, I can do this kind of like going back to the arrangement of what I had immediately earlier. But let's say that instead of taking the determinant right away of the inside numbers, say if I want to reduce the size of the absolute values of negative 100 as well as 20, I can factor out 10 once more, and upon doing so, I'm compounding the factoring, so this time around lowering the coefficients in both the top and bottom rows. The outside number is no longer 10, but factoring out 10 once more, I'm going to have 10 times 10, which will be 100. And now the inside numbers will be negative 10 and 2, 3 and 4, and looking at taking 100 times the difference of the cross products. So you're going to have 100 times what is going to be the quantity of negative 40 minus 6. And so we're going to have 100 times negative 46, which will be negative 4,600. Now, in looking at finding a determinant using elementary column operations, okay, and now we've been accustomed to working with rows, okay, but in the case of working with columns, okay, now we got here, we have a matrix A that is a 3 by 3, and we have 305 at the top, 147 in the middle, and negative 265 on the bottom. And we want to, in a sense, create the presence of zeros to potentially reduce the amount of work that would be involved in looking at the determinant of this particular matrix. Okay, and so again, we have with the signs of the cofactors, okay, for a 3 by 3, like the top row would be a plus, minus, and plus. And now, looking at what we have here for the determinant setup, okay, notice we have the presence of a 0 in the top row, and let's say that if I wanted to create another 0, okay, just using column operations while keeping the middle 0 at the top, and what I can do here, say that something I can just kind of pick apart is that with the last column, I can just say that I can have the middle row last column value at 0. So what I can do here, like 7 minus 7 times 1 is 0. And so I could just take collectively, subtract 7 times the first column from the third column. And we have in this development, okay, so I've got 3, 1, negative 2 for the first column, 0, 4, 6. And for the last column, I'm going to have 5 minus 21, 7 minus 7, and 5. And what's going to be plus 14. And so looking at what we have in this determinant, let's say if I don't use any more column operations and just kind of follow through from here. So I'm going to have, looking at the value of 3 times the minor of the first row, first column. So I'm going to have 3 times the 2 by 2 determinant, where we have 4 and 0 at the top, 6 and 19 at the bottom. And we have minus 0, okay, so that doesn't do anything for us. And then for the last column. Okay, so you have plus negative 16 times the minor of the first row last column. So you have left exposed 1 and 4 at the top, negative 2 and 6 at the bottom. And so we have for the minor. Okay, so you got plus 3 minor. The first row, first column has a value of 76. And then we have minus 16 times the minor of the first row last column. And that value is going to end up being 14. And so we're going to have 228 minus 224. And this result ends up at 4. And let's say that if I were to continue, and let's say that if I had 305 changed over to 30, 0, and 50, it's going to be the same operation, but this time around I'm going to factor out 10 in reference to the first row. Okay, so I'm going to have 10 times 305, 147, negative 265, and basically it's going to be the same exercise all over again, except we are now multiplying by the factored out 10. Okay, so where we had just 305, 147, negative 265. Okay, this time around we're going to have 10 times that amount. We're going to have 10 times 4, and that's going to end up at 40. So the difference being from the 10 that factored out from the top row. Okay, same work, but just the factored out 10, which we would again end up multiplying the value from the determinant established inside. Okay, now looking at column operations for other, let's say 3x3 determinants, and there are varieties of approaches that can be taken. And let's say that we have a 3x3 matrix where we have A consisting of 3, 6, 9, and we have also 4, 0, 1, 8, 3, 7, and we have one approach we can take here is to subtract 4 times column 3 from column 1. Like make this 4 into a 0. Okay, so if I have like 3 minus 4 times 9, okay, that's going to be negative 33. 4 minus 4 is 0. 8 minus 4 times 7 is going to be 8 minus 28, which is negative 20. And so we have this arrangement. And let's say that if I were to subtract 1.5 times column 2 from column 3, okay, you're going to have, like in this one case, you have 9 minus 9 is 0, 1 minus 0 is 1, 7 minus 1.5 times 3 will be 7 minus 9 halves, so there'll be 2.5. And so just looking at what we have now, so we have we'll have like what's going to be negative 33 times the first row, first column minor, and the value of that minor is going to end up being negative 3. And we have minus 6 times the first row, second column minor. Okay, so we got 0, 1, negative 20, and 2.5. And the value of this minor is going to come out to positive 20. And so you have 99 minus 120 comes out to negative 21. And let me pause right here. Again, there are varieties of approaches that can be taken. Notice that the top row has a common factor with 3. And so I could have factored out the 3 and have like 3 and 1, 2, 3 and just followed through from that perspective. And another approach that can be taken. Okay, so if I did not think still factoring out 3 from the top row, which I still can, but I just keep the numbers as they are. And let's say that if I wanted to make, say like the number 3 here in the top section as a 0, what I can do here is I can take column 2. Okay, say like half of 6 is 3, and 3 minus 3 is 0. So I can take half of all of the second column and subtract from the first column. So we have with the second and last columns still fixed. Okay, I'm going to have the first column to be changed over to 0, 4, 6.5. And then looking at subtracting 1.5 times column 2 from column 3, just like what I did moments ago earlier. Okay, so you're going to have that bit of history to repeat. And notice upon doing so, I'm going to have only one number in the top row, and that's going to be with 6. So again, after subtracting 1.5 times column 2 from column 3, you got 9 minus 9, 1 minus 0, 7 minus 9 halves, still at 2.5. And so I'm going to have left over the negative of 6 times the minor of the first row, second column, and the value of that minor is going to end up at 3.5, and negative 6 times 3.5 is still at negative 21. So I get the same result. And another way to, let's say that through the lens of row operations, okay, let's say that, again, 369401837, and let's say that if I want to make the 8 into a 0, and what I can do here, I can subtract 2 times the second row from the last row. Okay, so we have like 8 minus 2 times 4 is going to be 8 minus 8, which is 0. 3 minus 0 is 3. And 7 minus 2 times 1 is going to be 7 minus 2, which is 5. And then if I make what I have here, say working with column arrangement, say if I subtract 3 times column 1 from column 3, again, 9 minus 9 is 0, and 1 minus 3 times 4 is 1 minus 12, which is negative 11, and 5 minus 0 is still 5. And just looking at what we have here, so got with the cofactor signs, again, have in the top row have a plus minus plus arrangement. So got the plus 3 times the minor of the first row, first column, and the minor value comes out to 33. And I have minus 6 times the minor of the first row, second column. Okay, and so that's going to end up with a minor value here of 20, and here we have 99 minus 120, which comes out to negative 21. Again, I could have factored out 3 from the top and have like 3 on the outside, like 1, 2, 3, 4, 0, 1, 8, 3, 7, and just follow through with row and column operations. And I'll give you an instance in just a moment. Now, in the case of what we have regarding matrices and zero determinants, now, if A is a square matrix and any one of the conditions below is true, then we're going to have the value of the determinant of A equal to 0. And one of the conditions is if we have an entire row or an entire column to consist of zeros. Okay, and so if we have a matrix A, and notice we have like the third row consists entirely of zeros, so that determinant is equal to 0. And let's say that if I have A to be in the form of matrix B, and notice we have the third column consists of all zeros, and so with that first property applied, okay, it turns out that the determinant of that particular matrix is equal to 0. Now, a second condition is going to be where we have 2 rows or columns are equal to each other or identical. And notice we have for the matrix A, we have an identity between the second and third rows. Anytime you have an identity between rows or columns, the determinant is equal to 0. And likewise for matrix B, you have an identity between the first and the third columns. And so that determinant is equal to 0. And furthermore, if you have one row or column to be a multiple of another row or column, and we have in the case of matrix A, okay, now the determinant is equal to 0 on the basis of this third property. It could say that the third row is going to be 2/3 the value of the elements in the second row, or just the other way around, you could say that the second row elements will be 1.5 times what we have in the third row. Okay, so you have a multiple relation, and notice for matrix B, okay, the third row elements will be -2 times the first row elements throughout. So you have like 1 to -2, 9 times -2 is -18, 0 stays at 0, and 3 times -2 is -6. And so we have with that property, we have the determinant of B to end up at 0.